Our eyes, our windows to the world around us, have long observed multitudes of creatures moving at myriads of directions. Our eyes, gazing at the stars every night, have observed how these twinkling specks have slowly marched across the night sky in unison. Eventually, a method of describing these movements has been formulated, which is now used in several fields, prominently physics. This is the topic of this video. Any introduction to physics requires us to define motion using a mathematical framework. To lay down this framework, we first define motion. The thing is, we unconsciously observe motion with reference to another body or feature. We can formalize this by defining a so-called reference frame. A reference frame is an abstraction of our vantage point where we base our measurements from. We often define a reference frame as a combination of a coordinate system and a stopwatch. The origin of the coordinate system is in a body or a feature that we want to base our measurements from. Finally, we track a moving object by measuring its location relative to the origin in successive time intervals. The location of the object relative to the origin is called the position. Motion, therefore, is defined as the change in position over time. This has been done for thousands of years by various civilizations in tracking the progression of the stars. The astronomers use a spherical coordinate system to mark the location of the celestial bodies while relying on the periodic motion of the sun and the moon as stopwatches to mark the time intervals. Over time, they managed to see patterns in the procession of heavenly bodies in the night sky. They used these patterns to predict the position of the planets, eclipses, and eventually some regular comets. Let's go back to our reference frame. As we track the motion of the object, it is possible to take note the changes in the position over time. We mathematically define this as displacement. Unlike position, displacement is independent of the reference frame used. We can define average velocity using the concept of displacement. We need to measure the position at time t sub 1 and at t sub 2 and then get the difference in the positions within the time interval. That is average velocity. Another way of defining velocity requires you to make fine measurements of the position in short intervals so that you can construct the so-called position function. Getting the time derivative will give you the velocity function. You can get the instantaneous velocity by substituting a specific time to the velocity function. Sometimes, you don't need the relative mathematical complexity of the velocity to describe the motion of the object. Let's say an object moves along a straight line. In that case, we select its starting point as the origin of a reference frame, then measure how far the object is from its starting point. Or maybe the object moves along a meandering path, and we need a sense of how fast the object moves along it. Displacement and velocity will not suffice. We need to consider the length of the meandering path. For this, we define distance as the length of the path taken by the moving object over time. We then define speed as how fast the object moves along this path. We note now that the velocity is a vector quantity, while speed is a scalar quantity. Thus, in order for the velocity to be constant, both its magnitude and direction should be constant. Interestingly, the magnitude of the velocity is the speed of the object. Our description of motion is not complete without defining acceleration. Acceleration is basically change in velocity over time. We can apply the similar method in defining velocity to define average acceleration and instantaneous acceleration. Basically, the most important physical quantity in describing the motion of an object is its position. You can derive from the position its velocity and acceleration. Barring changes in the system, you can also predict future motion using the position function. Can we instead start with the acceleration function and then figure out the velocity function and position function? Of course, by integrating the acceleration function to get the velocity function and then integrating it again to get the position function. However, you need to apply the initial values one at a time to arrive at the correct functions. We have now defined position, displacement, velocity, distance, speed, and acceleration. Let us consider one important question. Can the reference frame move at the same time? Yes. All motion is relative. We make assumptions when describing the motion of an object. For example, we consider the Earth to be immovable compared to the small objects moving in its surface. However, we know that Earth is moving around the Sun. The Earth's motion manifests itself as retrograde motion for planets whose orbits are located farther than that of the Earth. Eventually, astronomers realized that the Earth moves around the Sun instead of the Sun moving around the Earth. Not only that, the reference frame can also be accelerating. The physical manifestation for this case is the existence of a fictitious force. If you are riding a vehicle that is turning around a curve rather quickly, you would feel like you are pushed by a force to the other direction. We call this the centrifugal force. Long-range winds in our atmosphere also feel this. We call this the Coriolis Force. This is your introduction to motion. I hope you learned a lot from this video. Thank you for listening.